What's up everybody, I'm Derek, this is Rocking eForge, and today I'm going to be covering the fundamentals of blacksmithing for beginners. Now the first fundamental I'd like to cover is that of personal protective equipment. Now you do not have to have a big thick leather apron like the one I made and I'm wearing in this video. In order to protect yourself, I have simply burnt through too many t-shirts with the forge scale and the sparks and things coming off of pieces of steel I've been hammering on, to the point where I decided a nice extra protective layer would do me some good. However, the first thing I am going to tell you you absolutely need when blacksmithing is a good pair of safety glasses. Now, as I previously implied, there is enough forge scale and sparks and things flying off of hot pieces of steel when you're hammering or grinding or cutting that you absolutely need something to protect your eyes while all of that stuff is flying everywhere. The last thing you want is to get a shard of steel in your eye or otherwise damage your vision while you're doing such a fun hobby as blacksmithing. Now the next thing I'm going to tell you you absolutely need to have is a pair of earplugs or some sort of hearing protection. Cheapo set of disposable earplugs works totally fine. It is simply too important to protect your hearing from the high frequency sound of hammering on the anvil over and over and over again over the course of potentially years of your life to not protect that vital sense of hearing. Now the next piece of protective equipment I'm going to talk about are gloves. And you're going to find as many opinions out there as people with respect to their take on whether or not you should wear gloves. There are many people out there who wear gloves on both of their hands. I personally wear a glove on my non-hammer hand, and there's a couple of reasons for that. First of all, I simply just like the feel of the hammer in my hand without a barrier between the hammer and my skin. Personally, just get better feedback from the hammer that way, and I can more readily feel what I'm doing if I don't have a glove on my hammer hand. Additionally, I personally find I get fewer blisters on my hammer hand when I'm not wearing a glove because the material on the glove can provide more slippage and more wear on my hands at least than when I actually just simply use a proper grip on a nicely made hammer handle. Now, I personally wear a glove on my non-hammer hand because I am frequently using pieces of steel long enough that I can heat the end that I'm working on in the fire and hang on to them with my non-dominant or non-hammer hand, which makes control of that piece of steel much more fine than when I'm using a pair of tongs. However, if you do use tongs all of the time, there's no reason for you to necessarily use gloves, other than the fact that depending on how long you are using the tongs, they can still get hot. Now, I tend to wear a glove on my non-hammer hand simply because I do a lot of that work without tongs, and because honestly, it's just become a habit at this point. However, there are a couple rules that I follow with the gloves that I wear while working on hot steel. Many people may disagree with me, but personally for me, those rules that I follow are they are always leather gloves, and they are always gloves that are fitted to my hand, but not so tight that I can't shake them off one-handed. For me, that's a fundamental rule for selecting the gloves that I wear, simply because sometimes you get the fingers of the gloves or the palm of the gloves very hot inadvertently, and you don't want that heat to stay in contact with your skin, or if you have forge scale or something drop down the back or the front of your gloves, you should be able to whip your gloves off with short notice or very quickly without having to grab them with your other hand, such that you minimize any burning that might occur or avoid it altogether if you are quick enough. I want to turn your attention to two books that I will be using as reference for the techniques that I learned in this video, and that is Skills of a Blacksmith Volume 1 by Mark Asbury and The Backyard Blacksmith by Lorelei Sims. Now, I am entirely self-taught in the art of blacksmithing, and it is because of books like these and YouTube videos out there that I learned the basic techniques that I am about to show you in this video. Now, the techniques I'm about to show you are, at least in words, written in these books, which is what I'm going to reference when I'm describing them to you and the importance of mastering them. And I just wanted to make sure that people getting into the art understand that books like these are incredible resources for learning the craft. These books will be linked in the description below. They are not Amazon affiliate links. I will make no money. I simply want to raise awareness on the excellent resources that we have when getting into this craft. All right, so while the forge heats up, I'm going to give you kind of an introduction of what I'm going to cover in this video, and hopefully I have the forethought to actually put the little chapters in the video so that you can go back and watch each of the fundamentals that I cover. Now, the lessons I'm going to be covering in this video are going to be tapering, spreading, upsetting, bending, and scrolling. Now, those 5 fundamentals are going to make up the foundation upon which you are going to build your blacksmithing skills from here on out. So without any further ado, let's get rocking. A bonus lesson I'm going to teach you in this video is simply to forge your steel at the right temperature. Now, the proper temperature for forging is at a light orange color or hotter, and you should never be forging on a black heat. The lowest temperature you should be forging at is this, really it's already reached nearly black at this point, but a dull red temperature is the lowest temperature that you should ever be forging steel at. And the reason for that is because depending on the alloy of the steel, medium or low carbon steels don't tend to have as much trouble, but when you get to higher carbon steels, the colder you forge, the more likely you are to induce cracks in the steel and then ruin the piece that you're working on. All right, so leading into the first lesson here, I forged the tip of this down into just a simple square, and the first lesson we're going to be covering is the taper, or tapering. Now, the first subset of the tapering lesson is going to be for drawing out forward tapers, and for that we are going to come to the far face of the anvil. Notice I am standing closest to the near face. We're going to put the edge of the piece of steel on the far face of the anvil, and we're going to use what's called half-on, half-off blows with our hammer face at a slight angle in order to forge that down into a blunt taper, and we'll see that in the next heat. Now, we are going to keep this piece of steel flat on the anvil, and we're just going to forge what I call a two-sided taper. And you can do this as slow or as fast as you want. Just work on that control. That's the bigger piece when you're just getting started, learning that hammer control. Now see, I'm already forging cold. But the fundamental that you're practicing here is angling your hammer slightly so that you're getting that taper. And if you are keeping the piece that you're forging on the flat face of the anvil, you will get a two-sided taper at the angle your hammer is striking at. So if you want a blunter taper, you've got to strike more toward the end of the bar or the piece of steel that you're using, that you're forging on, rather. And if you want a less blunt taper, you simply have to reduce the angle of your hammer in relation to the face of the anvil. Now, backing up slightly, half-faced blows, or when the hammer is half on the face of the anvil and half off, is a fundamental tenet of how to forge a taper. It tends to be the most efficient, and the reason you tend to use those half-faced blows is because any overhang of your hammer face over the piece of steel that you're working on won't strike and dent or chip the face of your anvil. You can get down to a very fine point on that piece of steel by using those half-face blows. Now, as you're starting out, don't really focus on how nice the piece of steel looks as you're working on it. It's going to take a while for you to build up those hammer skills, and it's not a huge deal if you don't get them right away. So the other fundamental tenet of forging tapers is simply to start blunt and then work that taper back into the piece of steel that you're working on. Tapering steel or drawing out steel will always lengthen it because you are reducing the cross-section of the steel that you're working on, such that as you reduce that cross-section, it is spreading the steel lengthwise out away from your tongs, and as such you're getting extra length out of it. The best practice is to start at the tip and get the tip of the taper down pretty much where you want it, and then work that back toward your hand so that you aren't wasting a bunch of steel, and once you get to the desired length of the taper, you can cut it off or otherwise start on the next portion of the project. I'm going to show you how to forge a simple leaf in the process of showing you tapers, because it's a great project to work on your tapering and your spreading skills, and we'll get to that on the second lesson. Tapers don't need to start at the end of the bar You simply have to continue using the same angle and half-faced blow fundamentals as I taught previously. And that fact is how you tend to isolate a chunk of material at the end of a piece of stock in order to start a lot of projects. Now, this is the normal way that I forge a leaf, by starting with a forward taper here at the end of the leaf, and then starting the stem using an additional forward taper by laying the material that will become the leaf off the edge of the anvil and continuing to use those half-faced angle blows in order to forge that taper. Now, you can make that taper more intense by angling the piece of stock as much as you are angling the hammer. That will drive that taper on both sides, as opposed to making it just flat on one side and then angled on the other. Your ability to do that will come with experience, and for the time being, I recommend just leaving it flat on the face of the anvil while you forge in your tapers. Now, the next portion of the tapering lesson to learn here is how to forge a reverse taper. Now, this follows the same basic principle as forward tapers, in that you are using half-on, half-off blows. You are simply doing it at the near edge of the anvil in order to forge that taper in the opposite direction as you would using the far edge of the anvil. Now, this gets a little more complicated because angling your hammer can be a little more uncomfortable at this edge. This is where I find that angling the piece tends to be a little more fruitful for me. But that is simply up to your own personal preference, and it depends entirely on how comfortable you are with each technique. Now, once you get a taper started and you're trying to blend that taper into the rest of the piece, that's when you can start using full-faced blows on the face of the anvil and just simply angle your hammer such that the taper continues up into the piece. And then eventually you'll probably blend it into a just square cross-section or a forward taper to the point where you've kind of finished that piece up and can move on to the next step. So I'm just gonna go ahead and do that. I'm gonna blend this reverse taper up into that forward taper, make sure everything's all square. Then I'll get into the next lesson of this video. Side note, I am really enjoying this pair of tongs that I just finished forging, and they're highlighted in my previous video if you wanna go check that out. Shameless plug. Now you'll notice, as I was forging this taper back into the body, I continued to just kind of pull this out toward me. And that's because you get the most mechanical advantage by still using those half-on, half-off blows. And in order to efficiently use your heat, it still works to continue forging the steel while you are doing that. Now, you will get on the back side or the face side of the piece of steel, you'll get little ridges where the blow of the hammer forced the material down over the edge of the anvil, and all you have to do is come back in another heat and clean that up by simply just hammering those back into the steel. That actually forces more lengthening and more reduction in the cross-section of the steel itself, and actually speeds up the process. But you can absolutely still do this just on the flat face of the anvil, so don't worry too much about getting that perfect. Now, something you've probably already noticed while I'm forging is that I rotate the piece 90 degrees every time I hammer on it. Now, this serves multiple functions. Primarily, it simply just keeps the piece square so that it's in a regular shape. If I were forging this wider in one dimension than the other, I wouldn't be turning 90 degrees after every blow. I would simply be forging down to the thickness that I desired and then bringing that into the final dimension on the width. Now, the other thing that turning the piece 90 degrees every blow does, and what you're not seeing, is the fact that and I'll exaggerate it here, I am rocking the piece ever so slightly to bring as much of that piece off the face of the anvil and out of contact with the face of the anvil as I can, because the anvil is not nearly as hot as the piece of steel that you're working, and as such it is sucking the heat out of the piece of steel actively. Now you can, depending on how fast you're hammering and how hard you're hammering, actually maintain heat in the piece of steel that you're hammering on, but the anvil will always seek to steal the heat from the piece, and the less contact you have every split second that you have the steel when you are not striking, actually hammering or striking on the piece of steel, is every second that you get to maintain that heat in the piece of steel that you're working on. I'm taking this nice and slow so that you can kind of see the process, and I'll blend this forward taper back into the reverse taper a little bit as we go, but this is going to end up being a small leaf ornamented wall hook that I'm simply going to just kind of square out this middle portion, punch a hole, or I'm not going to worry about punching the hole on this video because that's not the focus. But it does highlight a lot of the fundamentals that I'm covering in this video, which is why I chose this project. Another thing that you'll notice is I tend to only like to forge while rotating 90 degrees in two directions. You can absolutely rotate 90 degrees every time. I just find that a little less comfortable and a little more unwieldy, especially when you're using tongs. But that will generally ensure, as long as you're using the same force in your hammer blow every strike, that will ensure that the taper is centered as opposed to favoring one side like this taper does. I tend to just find it more comfortable to rotate 90 degrees over and over again and then even out or bring that taper back to center toward the end as opposed to worrying about it. Both ways are totally valid, both ways totally work. Just do whatever you're most comfortable doing. All right, so the second fundamental lesson that I'm going to teach you in this video is spreading. Now you can spread a piece of steel in many different ways, and that is dependent entirely upon the geometry of the hammer that you're using and the geometry of the supporting face of the anvil or the swedge or whatever else you're using to support the piece of steel that you're spreading. So we're going to switch stock and hammers here briefly to demonstrate spreading. And the first thing to illustrate spreading is that if you are doing full face blows with really any geometry of hammer, whether it be the flat face of my rounding hammer or the rounding face of my rounding hammer, it is going to spread the steel outward in 360 degrees. Now the degree by which you spread the steel is impacted by the geometry of the face, but if you were doing full face blows without any angle on the anvil of your piece or any angle on the hammer, you are going to primarily be getting just a 360 degree spread. Now to further go into that, if you are doing full face blows, your steel will always widen and lengthen in the axes that are perpendicular to your striking axis. As you can see, this is a 1/2 inch square bar. This 1/2 inch square here. If you move all the way up here, you can't probably tell because the lines are so dirty, but we've got about a 1/16 of an inch extra width at the tip, and we've come down to nearly 3/8 of an inch in thickness, just based on the spreading of the flat face of that hammer. Now, this is one of the major reasons why you see me do the 90 degree turns back in the tapering lesson, simply because if you don't control how much that spreads, you're going to have to turn it on that side in order to bring that back into the thickness that you want it, unless you want the spreading, which does occur in many projects. Next thing we're going to talk about is the rounding face of the rounding hammer. All right, so I'm going to attempt to keep all things equal here. I did 7 blows. Those are all strikes using the rounded face of my rounding hammer, and regardless of them being full-faced blows down on the flat face of the anvil, you can tell that the mode by which I am spreading the steel is a little bit different than by the way that I was spreading the steel with the flat face. The rounding face of the rounding hammer still spreads steel in a 360-degree outward motion. However, because of the geometry of the rounded face of the hammer, you're getting as much fullering action as you are downward force into the piece of steel. Now that fullering action results in more pressure being exerted at the center of that face, which equally drags steel downward into the bowl you are creating with the round face of the hammer, as well as pinpoints more force in the center, forcing that extra material that is displaced to be in a more outward direction. All of that force at the face of the hammer into the piece of steel is going to be directly perpendicular to that surface area, but because the surface area is rounded, that force vector is going to be directly into the steel at the center and then slightly outward as you get further and further out on the face of the hammer. Something else to note here is that the face of the piece of steel that I actually struck with the hammer is slightly wider at this point than the steel that was supported by the anvil. Regardless of the entire piece widening slightly, this highlights that the force of the hammer, while it should be equal and opposite at the anvil, there is a bit of force attenuation through the steel, so you don't get as much spreading on the supported face as you do on the struck face of the steel. Now this can be a good thing if that's what you're going for. However, that's typically not desired, and that means that you have to alternate the faces that you strike using the rounding face of your hammer. Otherwise, you're going to get a very odd kind of taper back from the surface that you are striking down to the supported face of the steel. Now this also illustrates kind of the difference between the actual rounded face, the fullering action of the rounded face of the hammer versus a flat surface imparting the same amount of force. You're getting more spreading at the surface where the rounding face is striking than you do on that back face where just the simple flat face of the anvil is kind of quote unquote striking back, so to speak, against the steel. The next mode of spreading that I'm going to illustrate is what's called fullering, which uses either the cross peen face of my cross peen hammer or simply a tool called a fuller, which is, compared to the regular face of a hammer, a sharper but still rounded face of that hammer. All right, so now that you have seen the rounding face of the rounding hammer do its kind of fullering action, there still is a slight bit of lateral spreading, very local in this piece of steel, and that's primarily due to the extra pressure that you get from the thinner face of that hammer. Because the rounded face of this crosspeen exerts that force similar to the rounding hammer perpendicular to the contact point of the hammer, you will get mostly linear spreading perpendicular to the axis of the peen itself. So striking this direction on this piece of steel, it fullers into the steel deeper than you get with the wider fullering action of the rounding hammer, because pressure is force divided by area. The surface area of this peen is much smaller than the surface area of the wider hammer face, and because of that kind of requirement of the steel to spread perpendicular to the force, it is spreading linearly along the piece of steel, and you are getting more length than you are lateral spreading. So this is very useful when you are trying to draw out a piece of steel lengthwise and not get as much width out of it as you would with the other two methods of spreading here, and it comes in handy very frequently in most projects. The horn is another way to get a very similar action, and we've moved back to the rounding hammer here. And this is where you can really start combining the modes of spreading by using the mechanical advantage of a certain geometry of hammer, as well as certain geometries available on the anvil itself. The previous three methods of spreading simply use the flat face of the anvil as the support of the blows, and as such, there was not as much spreading seen on the supported face of the steel. However, in this case, I used the horn of the anvil as its own fullering face to sort of match the fullering action of the rounding hammer face. This is very nicely done if you match the radius of the rounding hammer to nearly the same radius as the point on the horn. And as such, you get spreading, as you can see, on both faces of the piece of steel. Now, because you are not using the flat face of the anvil as support, this actually converts the 360-degree spreading that you see from the rounding face of the rounding hammer to mostly a fullering action. Granted, you do still get some localized spreading at the face that is struck with the hammer, and that's primarily due to that attenuated force, and yes, a bit of still that 360-degree spreading action due to the geometry of the face. However, you get almost exclusively lengthwise spreading from the horn of the anvil, and this combination of geometries can be very useful when you are trying to draw out a thick or long piece of steel, because this actually speeds up the process that you would normally get at the flat face of the anvil. You can, and even should, use this concept of using not only the geometry of your hammer face, but the geometry of certain portions of the anvil to be its own kind of extension of this principle, in that you can use the edges of your anvil as a fuller in order to exert spreading on a certain side of the piece that you're working on, while not necessarily using the same fullering action with the hammer that you're using. So you can keep the side that you're striking primarily flat and actually use the geometry of whatever edge of the anvil that you're using to actually force a fullering action without even leaving the comfort of your anvil. Now, to quickly add here, you will get 360-degree spreading from the center of the strike of the ball peen hammer in much the same way that you do on the rounding hammer. However, in the same way that the fullering action of the cross peen is deeper than the fullering action of the rounding hammer, you'll get a deeper penetrating strike from the ball peen here than you do a rounding hammer, and as such you will get deeper and more localized spreading, which can be very useful when peening over a rivet, which is why I tend to use a ball peen for peening the rivets that I use for my tongs. Now, before I use the concept of spreading on this leaf, I need to give you a bonus fundamental here. Because I don't want the stem portion of this leaf hook to be fully square. Now, the bonus fundamental I'm teaching you here is generally colloquially known as the square octagon round rule or law. And that concept simply follows the idea that you are typically in some sort of square geometry or rectangular geometry when you are forging, simply because you are typically using the flat face of the anvil and the flat face of a hammer to do most of your work. In order to forge something round, you have to go from that square cross-section to an octagon first by forging in the corners of that square prior to getting the cross-section to a round state. Now, the reason I do this before I spread the leaf is because this gets a lot more complicated to get up close to the edge of this leaf here once you've spread it fully and the actual leaf edges come out much farther. Now, it's important here to get that octagon as close to perfectly octagonal as you can prior to taking this shape to round, because that will simply just make your round shape much cleaner. The actual concept you're using here is simply to strike all of the sharp edges back in toward the center of the piece, thus doubling the number of faces, but eliminating most of those sharp edges until you can just simply rotate around on the face of the anvil and kind of individually knock all of those facets back in toward the center. Now, this is one of the only times that I will condone lightly striking the piece while it's cold. This is what's called planishing, and it is simply striking the steel while it's colder so that you're not getting as much deformation, but you're knocking in those sharper corners and evening out the surface of your piece. Again, this should be very light. It should not be full force hammer blows, and you should absolutely be careful when doing this, especially with higher carbon steels. This can still induce cracks, but with lower carbon steels, like the one that I'm using here, it's not generally a big concern. Now that we've got the stem rounded, see if you can follow along and see what spreading techniques I use to forge the shape on this leaf. All right, the third lesson that I'm going to teach in this video is upsetting. And that is not a trigger warning, that is the title of the next technique that I'm about to show you. Now, what is upsetting? Well, other than your roommate stealing the pizza that you left in the fridge last night that you fully intended to eat, upsetting is a method of thickening a piece of steel wider than the original stock that you are using in a localized area by striking along the centerline axis of that piece of steel. The ability to upset a bar is typically limited to the length that is equal to the thickness of the piece of steel, which is where you should focus most of the heat of your flame, specifically where you are trying to thicken the material. Now, this is very frequently done at the tip of a piece of stock, trying to get a slightly thicker piece of material in order to shape it into a spoon or a scarf for a forge weld. However, it can also be pinpointed in the center or anywhere along the length of a piece of steel if you're using the correct techniques. Now, that is typically best done in a coal forge because you can get much more pinpoint heat in a coal forge than you can in a propane forge, which is what I'm using today, or with an oxyacetylene torch by literally pinpointing the heat in the area that you're looking to thicken. Now, this works along the same kind of concepts as spreading in that you are using force of the hammer blow to force material back into the actual parent stock and thus widening it in 360 degrees from the center of that blow. However, you are not looking to spread the material locally like you do sometimes in the actual spreading lesson. What you're trying to do is simply move that mass back into the tip or wherever you are trying to thicken that piece of material and thus make it thicker by forcing the molecules to literally rearrange themselves under the force of the hammer blow. Now, you will still get some localized spreading, which is illustrated nicely by a rivet, in that a rivet starts out simply just a piece of round stock on the non-head end of the rivet, at which point you upset that back into the mass of the rivet itself, and then peen that over to actually widen and spread the other side to create an additional head of that rivet and actually force the two pieces of a pair of tongs together. Now I'm going to show you my most usual way of upsetting bar, in that I use the anvil as a table to rest the actual hot piece of steel on in order to avoid much of that localized spreading that you get from the full brunt of the force of the hammer. Now, I got a little bit of bending, as you may be able to see from there, but I did manage to spread the tip of this piece of steel. It originally was just under a ½ inch either direction, and with the bending it's difficult to measure, but it is just at a ½ inch here. Now, I'm hoping that you can see a bit more of that bend that it took here, and this illustrates the reason why you only want to heat the portion of the steel to that orange color that you actually want to do the upsetting at, because the longer the piece of steel and the longer that heat up that piece of steel, the more propensity the steel has to actually bend, as opposed to moving the mass into the piece of steel that you're hammering on and actually widening the whole thing. This will require another heat just to correct and straighten the piece of steel back out before I do another upsetting attempt. Additionally, you really need to start with as stock straight a piece of material as possible before attempting this. Now, of course, the alternative to the previous method is to simply lay the steel on the anvil and beat down on it with your hammer. Which can result in a lot more upsetting, simply because of the attenuation of the force through the steel to the actual surface of the anvil. You're cutting out all of that extra steel in the way and isolating your blow directly onto the heated steel. However, unless your blows or your strikes are perfectly in line with the piece of steel, you tend to get more bending this way, which is why I tend to do the opposite. But an alternative to simply bringing it with tongs and holding it vertical on the anvil is, if you've got especially a very long piece of steel that you need to upset the end of, heat the piece of steel at the end and then just bring it to the anvil, as long as you can get a good grip and not slip down that piece of steel to the hot part. Always wear gloves doing this, but you can simply bring it to the anvil and beat down on the anvil like that with the piece of steel, and that will also result in upsetting of the tip of that piece of steel. There are many different ways to do this. You can also lock your piece in the vise, which tends to minimize the bending that you can get, and you can kind of cheat the system that way, so to speak, but you tend to get bite marks from the jaws of your vise in your stock because you are forcing it down into the jaws themselves. However, there are many different ways to do this, and no way is incorrect. It's simply a matter of what tools you have available, what techniques you have available to you, and what you are actually trying to do with that stock material. So the leaf hook project that I've been working on throughout this video doesn't require any upsetting, and as such, we are going to move on to the fourth lesson in this video, and that lesson is bending. Now, at its core, bending is simply striking the steel at a point where it is not supported by anything underneath it. This does not include the half-on, half-off blows, as I was discussing previously in this video. It is simply unsupported strikes on the piece of steel. This will prevent marring the steel at the point where otherwise you would contact. And these are not considered forging strikes. A forging strike would be fully supported by either the face of the anvil or the horn of the anvil. However, bending strikes are specifically not supported at all, and the strike is against a piece of steel with space beneath it. Now, that does not mean that you can't do bending on the face of the anvil. A strike made with a portion of the piece contacting the anvil, but the strike still being over space between the piece and the anvil face itself would be considered a bending blow. It didn't bend where I struck because this is the thinnest piece, but there would still be a bending blow, which forces a bend at the point where either you have the most heat, the thinnest cross section, or where you strike it, depending on many other factors. Now, as I just mentioned, this bending force that you're imparting is highly dependent on the cross section, the thickness, the material, and the heat of the piece of steel, and the geometry of the surrounding piece. So you will very frequently get a bend at the thinnest portion of the piece of steel that you didn't want while trying to bend a thicker portion, simply because the thinner portion will move based on the kind of whipping action or other forces throughout the piece that you're imparting into the piece while you're striking on other portions of it. But all in all, bending is simply done by striking over space as opposed to striking over a supported surface. Now, you can bend steel over the horn of the anvil as well, and it's very frequently considered a good idea if you are trying to preserve a decorative element, such as this leaf, to cool it before you actually start bending the piece so that you can strike on the decorative element without worrying about ruining it. Now notice that I am continuing to strike over space in order to continue to force that bend. And of course you have to note that you have to have the piece supported in a location other than where you are striking in order to induce that bend. You can induce twists in much the same way. And as long as the point where your piece that you are striking is not in contact with the anvil, you are not doing a forging blow, you are simply bending the piece. Now I'll probably have to remount that hole again, but all in all, that looks pretty nice. Now, it's worth noting here that if you drill or punch your holes in your pieces prior to doing any of this bending, it's very possible that the hole will end up squishing or elongating or otherwise deforming, and you may need to repunch or re-drill that hole in order to make it perfectly round again. All right, so now we have come to the fifth and final lesson of this video, and that is scrolling. Now, as it is, I don't have the time to forge many different styles of scrolls, and for the leaf hook project that I've been working on this video, I tend to like to use what's called a penny scroll, or simply a square tapered scroll as a decorative element prior to actually finishing the bend for the hook itself. Before we actually start the scrolling here, it's worth noting that penny scrolls especially look best when you have a nice smooth taper to a relatively sharp tip. Now I'm demonstrating here that you are still able to forge a taper even if you're not at the far edge of the anvil, and the biggest reason for that is because now that I've got the leaf and everything curled, I have the actual piece in the way and I don't want to bend this while I'm working on it. So I'm just slowly working down this taper on the flat face of the anvil, just slowly necking down that material until I get to a nice tip, and then we'll get to the scroll. Now the concept of scrolling tends to work along the same lines as bending, with a couple exceptions. Typically, I like to use more of a grazing blow that more swipes along the material than a blow that strikes the material at more of a 90-degree angle. And as you just saw, I am continually shifting the piece further and further off the edge of the anvil so that you get kind of a continual spiral, so to speak, of steel. Now once you have this to roughly 90 degrees, I'm going to heat this up again, but you can turn this back so that the point is sticking up and continue striking in line with the axis of the material in order to further refine that, and then also strike down on the point once it's curled over enough to tighten up that spiral to make your final scroll. So we're going to do that in the next heat. This is such thin material that it's really easy for it to cool down very quickly, unfortunately, so you may have to do this in a couple of heats unless you're very efficient with your movements and not talking to a camera like me. Now it's worth noting here before I move on that if you are doing this on the end of a hook, you have to premeditate the direction that you're actually scrolling this over. And what do I mean by that? Well, what I mean by that is this hook is going to bend in this direction away from the back and toward the leaf. And as such, I want this scroll to be in the opposite direction so that the final product will scroll away from the main body of the hook and give it that kind of nice decorative touch. Now you can get away with not doing this and messing it up by just simply putting a twist in your piece just down from where the scroll is, which is what happened here. None of us are perfect, and we all make mistakes, and part of the fun of blacksmithing is figuring out what to do with your mistakes once you've made them. Your control of the heat of the scroll also will depend, or will determine how fine the scroll ends up. And you can refine that shape just by striking effectively perpendicular to the widest portion of the scroll in order to sink it down further. Now, I like to have my scrolls kind of contact the piece, but I like the tip to be a little more closer to 90 in a full spiral rotation. As such, I'm going to bring that back to the edge of the anvil and lightly hammer that into a more 90-degree orientation before closing this up. And you can still do this fairly cold. It's just not typically recommended that you do it fully cold. I have broken off scrolls by doing this too cold, so just word of caution to everybody. Now we're going to go back to the concept of bending here. I'm going to cool that scroll, and then we're going to simply support the hook where I want it to bend. And bend that to its final shape. It's really important to note here that I cooled the scroll so that I didn't damage it by striking on it while making this bend. However, and I don't think I covered this during the bending section of this video, this is not something that you should do with anything other than mild steel. If you're using carbon steel to make bends and scrolls and things like that, you will end up hardening the portion that you quench in the water, and it will either break off entirely the next time you hit it with your hammer, it'll crack, or it could even shatter in the water itself, simply because you are hardening that piece of steel. This is a piece of mild steel which does not harden even when quenched in water, and as such, that's not a concern here. But if you are doing this with a carbon steel, that's not something that you should do. Now, one final bonus fundamental here is going to be brush your work when it's finished. Get yourself a nice farrier's brush, or simply just a well-worn wire brush, to brush off any rust and eliminate as much of the forge scale and residue that you get from the forge from your finished pieces. It makes the finish that much nicer. And once I've given most of my projects a good brushing, I like to use a coating of beeswax to seal it off from any rust. Make sure you're doing this when it is cool enough, otherwise the smoke will burst into flames. I know by experience. And this also gives it a nice black finish, which I think looks pretty darn nice. This does need to be done hot, but again, do not do this so hot that the smoke actually bursts into flames. I have done that a number of times in the past, and it can be a bit surprising, to say the least. And that is going to do it for today's video. I do sincerely hope you learned a lot during this video, and I hope you enjoyed it, to say the least. If you did enjoy this video, please drop a like, leave a comment, hit subscribe, ring that notification bell. If you want to support me in the channel further, please consider becoming an honorary striker on my Patreon. That link is in the description below the video, or consider becoming a member on my YouTube channel. And as always, keep on rocking.